Hello, this is Matthew Feingold. This is my Game Engine 3 final project video. What you're seeing right now is my animation skinning skeleton system with compression going on, and I kind of just wanted to talk about compression first. So in my scene right now, I have 2 copies of my teddy and 2 copies of my humanoid. The ones in the middle are the regular ones, and the one on the outside, the ones on the outsides are the compressed. So this one is the compressed teddy bear. This one is the non-compressed. This one is the non-compressed humanoid, and this one is the compressed one. I purposely went with slightly higher rates of compression so you could sort of visibly see some of the compression. This one's the most obvious with the skeleton. He kind of slides backwards here a little bit, whereas with the non-compressed one he takes some steps back. Just like last time, I have full speed controls for forward and backward. And I can switch up the animations. I don't have blending. It's not something that I had time to get to, but with the systems I have in place, it wouldn't be much to add. So that's something I'm going to work on. Anyway, so taking a look at some of these compression rates here, I'm getting anywhere between kind of 3 to 10 times for some of these. I can even pull up the calculator and do some quick math here. If we look at this one, the idle, which is currently playing on the teddy bear, the idle regular one on the right here is 134 kilobytes, and the compressed one is 23, giving me roughly almost a 6 times compression on the compressed one, and it's hard to spot the differences here. The main thing I noticed is that on the compressed animation, the teddy's head here on the left kind of keeps on looking to the left, whereas there's a distinct stop here on the right one in the uncompressed. Other than that, it's kind of hard to spot the differences. And a very high compression rate is this. Oops. Is this shot, here it is, the shot shot animation. So I'll turn it, that's this one that we're seeing right here, and this one, it's not quite as easy to see the compression here, but if we do the quick calculation, the original was 1050 kilobytes, and the compressed one is 102 kilobytes, which gives us over a 10 times compression rate. And the fidelity of the animation still stays, pretty true. You might find some inconsistencies there the higher the compression rate that you go, but I think it's looking pretty good for that big of a savings. Anyway, I have I guess I'll backtrack now and just talk about skinning. I put my Blindfong lighting on my models so I could kind of see, hands in front of bodies and things a little easier. I have the animation processing happening in compute shaders on the GPU. I can take a look at that really quick. Let me stop running this. I have a couple diagrams we can look at. This being the main one. This is my animation class diagram for my animation system. Essentially, I have this animation object here that has a reference to a skeleton. It doesn't own it. The skeleton is owned by a skeleton manager. And then it owns a linked list of clips, and each clip has all of its frame data. And what the animation update will do, I originally had it processing on the CPU, so I kind of just made another private function to keep the original functionality if I wanted to go back. And I set that with a Boolean to say if I want to do GPU or CPU processing. But I abstracted these shader storage buffer objects into their own classes, and I store them here in the animation object, and I also have two here in the skeleton. And during load content for the skeleton, the two SSBOs get stored here and never touched again. They just get loaded up once and then referenced later. And then here we have these three SSBOs where these two are acting as the result buffers of my two compute shader stages for the animation update, and then these two are the keyframes used to interpolate to find the current keyframe. So I essentially have two compute shader stages. And before I do this, quick look here, my shader buffer object basically is pretty straightforward. I just wrapped the OpenGL functions for example, bind layout. I'm able to specify the binding index, which is what you use in the GLSL file to kind of declare the buffer in there. I wrap my push data and mapping and unmapping, all that good stuff. Anyway, so in my animation update, we can take a quick look at this. I'm passing in the two keyframes and the interpolation factor because in my process animation function I do my loop to find my two keyframes that I want because I don't really want the compute shader having every thread looping. I think it's a waste. I'd rather just do it once on the CPU. So I do that once, and then I pass the keyframe data and the interpolation factor to either the CPU or the GPU function. And on the GPU, I just pass in a couple uniforms here, and then I am able to bind or push my data for my keyframe A and bind it to layout 0, and push my data for keyframe B, bind it to layout 1, and then I bind this local bone matrix output buffer, which I kind of push empty, like 0 data into it on construction of the animation object so that it's ready to go. And then I find the global group count by taking the number of basically, this is the number of bones, but take the number of elements in the buffer and divide it by how many local threads the compute shader is going to run, which allows me to figure out like how many global groupings do I need, because it's pretty much saying each group takes care of this many, so how many groups do I need? And I am using this ceiling function so that if this division ends up with a floating point number, I round up. And then in my GLSL file, I kind of check, if my thread ID is within the range of the buffer, because that can result with going out of bounds there. So, and then I use memory barrier to wait for compute shader to be done, and then this does the interpolation. And on compute shader stage 2, I pass in a couple uniforms. These really just specify the X and Y range of my hierarchy table, which I use to perform the game object update, essentially. And then I bind all of my SSBOs that I need. So this is the result of compute shader stage 1. These two get initialized on construction of the skeleton because this is static data, the hierarchy table and the inverse pose matrices that you need for the skinning equation. And this is the output buffer that everything will go to. So I read the hierarchy table to update all of the bone local matrices into the world, and I also multiply it by the inverse pose matrix and store it here so that it's pre-multiplied for the skinning. And then I wait for that to be done. Don't mind this, that's a test. And then what I have a diagram for this. In my graphics object, my graphics object skinning points to an animation object, and it will end up using this final result SSBO from the Compute Shader Stage 2 to do the skinning. So we can see if I go to here where you do your usual set state stuff, I have the regular uniform buffering the projection view and world matrices. I have my lighting information. The only difference is here I'm binding this SSBO that contains the bone world times the inverse pose matrix, so that my skinning equation no longer needs to be bone world times bone inverse pose times the position times the weight. It's just kind of the result from this buffer times the rest. So doing that saves computation, because the compute shader will essentially do that multiplication, the world times the inverse, once per bone, while the vertex shader might need to process the same bone multiple times, so it's doing a bunch of extraneous multiplications if you do it that way. Anyway, so that's really most of it. I think I'm probably running kind of long here. You can take a look at my shaders in my project on Perforce. They're here. I have compute skinning 1 and 2, and I have my skinning GPU, vertex shader, and fragment shader. The fragment shader was just basically the fragment shader for Blinn-Phong lighting. It doesn't really change much from doing skinning on the CPU or anything else special. The vertex shader is really where the magic happens, where you're taking the inverse here from the SSBO. So anyway, oh right, I also save the bone index and weights as in VBOs, and the way that the vertex shader kind of parses the VBOs, if you save them as vec4s, I get 4 bone indices and 4 weights, which is what we wanted to limit the number of bones our vertices can be weighted to. So it works out nicely to kind of index into them X, Y, Z, W here and here. So yeah. Anyway, don't mind all the commenting. That was debugging, and some of this is Blinn-Phong lighting. Anyway, alright, thank you. That's it for this video.